Hey everybody. So today we're going to go over part 2 of the orange equations. This is going to be 3 example problems where we're going to solve some orange equations. Now, we'll start off first with the indestructible bullet. An indestructible bullet, 2 centimeters long, is fired straight through a board that is 10 centimeters thick. The bullet strikes with a speed of 420 meters per second and emerges with a speed of 280 meters per second. What was the average acceleration on the board? How much time was the bullet in contact with the board? And are there any ambiguities in the givens worth discussing? So we'll do these in order. First, put that down there. So let's first write down our givens. Let's see, we have the bullet is 2 centimeters long. Okay, so we've got bullet, 2 centimeters. Then we've got the board. Board is 10.0 centimeters. It strikes with a speed of 420 meters per second, so we'll call that V naught. And then it exits the board at 280 meters per second. At 280 meters per second, so that'll be our final velocity. Now, so what was the average acceleration in the board? So first, let's figure out which orange equation we need to use. Last time in our orange part 1 video, we went over the 3 orange equations and why we need to carefully choose which one we use, because we may have a given that's not in that equation, right? So first, it's talking about acceleration as it travels through the board, right? So we can call the board's thickness delta x. Now, it's going to be important that we keep all of those givens straight, because here at the bullet, we don't right now have a use for the bullet's length. But we'll talk about that. That's going to come back up on number 3. So what was the average acceleration in the board? Well, let's go over all 3 of our orange equations. Okay, so we've got delta x equals v naught t plus 1/2 at squared. Then we have the final equals v naught plus at, and then we have v final squared equals v naught squared plus 1/2 at squared. I think that's right. Yeah. Yeah. What did I do wrong? Oh, I got them mixed up. That's what I did. No, this is v naught squared plus 2a delta x. Clean that up. Yeah. So that's plus 2a delta x. Okay. Now I hope I didn't mess up. If I did mess up, let me know. Okay, that looks good. So we have delta x, we have v naught, we have v final, right? And we are looking for a, which is average acceleration, right? That is not instantaneous acceleration. So let's go through here. We have delta x. We'll look at the first one. We have delta x. We have v naught. We don't have time. Can't use that one. So that's gone. Here we have v final. We have v naught. We're looking for acceleration, but again, we don't have time. So that one's gone. Here we have v final, v naught. Acceleration is what we need. We have delta x. So this is the equation we're going to use. So that's how you can determine which orange equation to use at any given time. So let's clean this up real quick, and then we will get on with the solution. So, and orange. So I'm going to scroll down to the next spot. I've got a work slide ready to go. If you need the information on this slide, go and pause right now, and then hit play in a second. So what was the average acceleration in the board? So we're going to use, I'll just bring that equation down here. F squared equals v naught squared plus 2a delta x, right? We've got delta x as 0.1 meters, 10 centimeters, right? V naught as 420 meters per second. The final is, what was that, 280? Let's see, we've got 280 meters per second. We need acceleration. So we've got our givens, we got the equation. Let's see if we can find acceleration. First, I am not a huge fan of plugging in those numbers and then doing the math immediately. Solve it using the symbols first, then plug in your numbers. The numbers is where you can get easily tripped up. So first, let's solve for A. We've already got A on one side. Let's isolate it. You've got V final squared. You'll subtract V naught squared over equals 2a delta x. Then we'll divide the 2 and the delta x over. So we'll have V final squared minus V naught squared divided by 2 delta x. Gives us acceleration, right? Now we've got V final, we've got V naught, we've got delta x. We know what 2 is. So now we can plug in our numbers. So we've got 280 squared minus 420 squared divided by 2 times 0.1. Now, I have my calculator. Let's hope it's got batteries. And it does. So let's do that math, shall we? We've got 280 squared minus 420 squared divided by 2 times 0.1. So what I got was a very large, very negative number. I got negative 490,000. Negative 490,000 meters per second squared. Now, first, should that acceleration be negative? Well, we know that it started out going into the board at a faster rate, and then it slowed down as it went through the board. So we know it should be negative. That means that it's slowing down, right? And should it be that large? Well, it lost, what is that? 140 meters per second while traveling 10 centimeters. So that's a very large acceleration to lose a lot of velocity in a very little distance traveled. So yes, that is an acceptable and understandable acceleration for that problem. Right. Let's go back up. Let's look at number 2. How much time was the bullet in contact with the board? So we have a new, let's update our givens real quick. We have a new given. So before we start this, let's say our acceleration negative 490,000 meters per second squared. Now I'm going to erase all of this work. If you need it, pause. All right, so we are now hunting for time. How much time was the bullet in contact with the board? So we need time. Now we can look at our orange equations again. We just got finished using V final squared equals V naught squared plus 2a delta x. If we're looking for time, that one can already be nixed because there's not even time in that problem, right? All right, so Next, we have V final equals V naught plus AT. Sloppy there. V final equals V naught plus AT. We have V final, V naught. We have A. There's T. That seems doable, and that's also the simpler of the two that we have left, because the other one we'd have delta X equals V naught T plus 1/2 AT squared. If we want to solve for T, we've got to use a quadratic to solve for the T, because we've got two of them and they don't even have the same exponent. So gone. We are going to use VF equals V naught plus AT. So before we plug in any numbers, solve for T. So let's isolate it. You've got V final minus V naught, and you'll divide by your acceleration to get T. Okay, and then we will plug in our numbers. You've got 280 minus 420 all over negative 490,000. Big numbers. So our time, if we plug that into our handy dandy calculator, so you got 280 minus 420 divided by 490,000. Okay. Very small time. So we have, and this should be positive. If you got a negative, you might have missed a minus or a negative value in there. So you get 0.0000286. I have a habit of putting slashes through those. Just a habit I have. Seconds. So 0.000286 seconds. You can also, when it's such a small number like that, I would use a metric. So we're going to use milliseconds. Cut off 3 of those zeros, we can say that's 0.286 milliseconds. Either of those is going to work as our answer. Okay. So now that we see the time, the acceleration really makes sense, because it went from 420 meters per second down to 280 meters per second in almost just a quarter of a millisecond. So that is a very fast change in velocity. So the magnitude of that acceleration, again, just being supported by further evidence. All right, that is all of our kinematic. That is all of our kinematic variables that we have. We have position, velocity, acceleration, and time. We have solved that. We've solved that problem to death. Now, number 3, any ambiguities in the givens worth discussing. Now, yes, I will erase. Oh, wait, scroll, then erase. I'm going to erase all of this. So if you need it, go ahead and pause. But there is an ambiguity in this problem that has caused a lot of discussion. And if we were in class, I'm sure that someone would have picked it up as well. The issue is going to be in that variable in that information we didn't use, the size of the bullet. So let's go back to this. So our bullet, right? Bullet is 2 centimeters, 0.02 meters long. Board is 10 centimeters long. Okay? Now, if we're talking about how long the bullet was in contact with the board, this can cause some issue. So we have a bullet. Well, let's get a better bullet, shall we? That's not much better. We've got a bullet that is 2 centimeters in size. Let me blow that bullet up so you can actually see the issue that we're talking about. So as that bullet hits the board, it hits the board right at the point of the bullet. Now let me put this a little bit more to scale. Okay, so if the bullet is 2 centimeters, that should be about 10 centimeters. So if the bullet touches the board here, it is technically in contact with the point, and then as the bullet travels through the board, right? Now it's been in contact with the board for 1 centimeter. Now it has been in contact with the board for 2 centimeters, right? Now, and we're not going to debate a whole lot on that we can see. Now here, we can say that the bullet has now been in contact for all 10 centimeters, right? We can look at the point of the bullet. Here, it is 1 centimeter through the board. Here, the whole bullet is inside the board, so it is 2 centimeters into the board. Now the bullet has been through all 10 centimeters of the board, but here, the bullet is still being slowed by the board. Would it be slowed by the board? There's still some friction there, so there is an 11th centimeter, and here that would be 12 centimeters that the bullet was in contact with the board, right? So last year, when we had this debate, we had people arguing that the bullet is in contact for 10 centimeters, 12 centimeters. We even had 1 or 2 individuals that were in the minority, but they even said that the bullet was in contact for 8 centimeters. But there is some ambiguity here because how long was the bullet actually in contact? Do we need to take into account the length of the bullet? These are all very good questions. And now we'll move on. I'm going to let you guys ponder on that one. Let it fester. And you tell me which one is the real right answer. So, next problem is about cheetahs. Cheetahs are the fastest land animal. Fact. The fastest animal sprinter is the cheetah, reaching speeds in excess of 113 kilometers per hour. These animals have been observed on a straight run to bound from standing start to 72 kilometers per hour in 2 seconds flat. What is the distance required for the cheetah to go from rest to 17.9 meters per second? Now, before we start, let's get some perspective in freedom units. Let's say that is 17.9 meters per second in miles per hour. So that is approximately 40 miles per hour. 17.9 meters per second, approximately 40. Now, 72 kilometers per hour, what is that? Let's see, 72 kilometers per hour. That is approximately 45 miles per hour. Okay. So we know that the cheetah can go from standing to 45 miles per hour approximately in 2 seconds flat. What is the distance required for the cheetah to go from rest to 40 miles per hour? Those are just to get an idea of those speeds in your more common vernacular. But for this math, all metric. So this cheetah, we have this data where we can find the acceleration, right? So we've got 2 parts to this problem. Here, part 1. Then here, part 2. Okay? So we'll do part 1 first. We need to know how fast is the cheetah accelerating from standing start to 72 kilometers per hour in just 2 seconds flat. What is the acceleration in that? Then we can use that acceleration to find the distance that the cheetah travels if it's going from rest to 17.9 meters per second. So, and this is the kind of method that you're going to have to use in this class. Sometimes you've got to solve for one thing before you can even consider solving for the next. Because if we start with part 2, it just wants to know the distance required for the cheetah to go from rest to 17.9 meters per second. Let's look at the orange equations that have distance in there. Okay, delta x starts off with the first one, delta x v naught t plus 1/2 at squared. Now already solved for distance, really easy. We have a v naught, right? It starts from rest. We know that it takes 2 seconds to go from start to 72 kilometers per hour. We want to know how long we would need here, the time it takes to go from rest to 17.9. There's also no final velocity in this, and we would need acceleration too. So this equation, bubkus, can't use that one. All right, let's check the other one that has position in it. We have v final squared equals v naught squared plus 2a delta x. There is the position we're looking for, right? We know v final. The question wants to know rest to 17.9. So we've got v final, that's 17.9. Rest, again, we don't have acceleration. That's why we're breaking this into 2 parts. If we try to jump the gun and find the distance without finding acceleration, we're lost, right? There's just no way to find that because you don't have enough information. So what we're going to do is we'll first find acceleration, then we'll find the distance required. So how do we do that? Well, let's get our givens up top. We have v naught is 0. V final is 72 kilometers per hour. We're going to need to do something about that, right? So let's break that down, shall we? 72 kilometers per hour. Let's see, 1 kilometer is 1,000 meters. So that'll get rid of our kilometers. Then 1 hour is 3,600 seconds. So that gives us meters per second. Let's see. So we've got, oh, that's not bad. 72 times 1,000 is 72,000. Oh, no, I won't be able to do that in my head. Dang. I thought I could. 72,000 divided by 3,600. So, okay, yeah, so that was easy. It's 20. Shouldn't have cowered. So V naught is 0, V final is 20 meters per second, and we know the time. The time is 2 seconds, okay? So we have our givens. We have V naught, we have V final, we have time. If we use the second orange, V final equals V naught plus AT, right? That we have all the givens and we have A right there waiting to be solved for. So we will do that right here. Let's rearrange that for A. You have V final minus V naught equals AT. Divide the T over. You have our final equation we're going to use is V final minus V naught divided by T equals A. Okay. We have that equation. Now let's plug in our numbers. Here, let's just leave it right there. Let's see. V final is 20 meters per second. V naught is 0, so you don't need to subtract it. Divide it by 2 seconds. So 20 divided by 2. Go ahead and pause and do that calculation. I'm sure that that'll take you guys some time to put into your calculator. Now that you guys are back from that pause, 20 divided by 2 is 10. So acceleration, 10 meters per second squared. So that is fast for a land animal. Holy smokes, 10 meters per second squared. That is some insane acceleration. Now that we have that acceleration, we can find the answer to part 2, right? So I'm going to, this slide's getting kind of messy. I'm going to go down a little bit further and we can reset our problem here. So we know the cheetah is accelerating at 10 meters per second squared, since we got our units to agree right from that kilometers per hour. This is asking if the cheetah goes from rest to 17.9 meters per second. Okay. And it wants to know the distance. Whoops. What is the distance that it takes that cheetah to go that distance? Now, I'm sorry, to accelerate to that velocity. So what we want here is we want an orange that doesn't have time in it. So, and we have one. Let's use VF squared equals V naught squared plus 2A delta X. So this one will not require time, which is the missing variable that we have here. We don't have that given on this part of the problem. So from here, first rearrange your givens. So let's solve for delta X. We've got V final squared minus V naught squared equals 2A delta X. Divide over your 2A. Okay, so there you've got divided by 2A gives you delta X. Okay. Now we can plug that in. Let's plug and chug. Remember, V naught is 0. So you don't need to worry about that guy. So we will take V final 17.9, square it, divided by 2 times 10. That I will not attempt in my head. We've got 17.9 squared divided by 20 is 16.0205. That's too specific for this, so we will use 16. Oh, that's 16.02 meters. And honestly, I don't think any of our numbers are that precise in this problem. No, we've got, yeah, so we can't even use 0.02. That's not even an accurate use of our sig figs. So that our answer is going to be 16 meters. So over the course of 16 meters, a cheetah can accelerate from a standing start up to approximately 40 miles per hour, which is insane. I know 16 meters is a long way, but that's still pretty impressive. I don't think any of our football players at Norman High could go from the, let's say we go from the end zone to the 15-yard line. None of them would hit 40 miles per hour. Unfortunately, if so, we could wreck some kids in football. All right, so that is the distance required for a cheetah to go from rest to 17.9 meters per second. All right. Last problem, a ball on a plane. No, not that kind of plane. This isn't like snakes on a plane. A ball starts from rest and it accelerates at 0.5 meters per second, another way to say meters per second squared, while moving down a 9-meter inclined plane. When it reaches the bottom, the ball rolls up another plane where after moving 15 meters, it comes to rest. So this is going to be a complicated problem. So let's draw it first. So let's move you over here. Okay, can I actually minimize you? Oh, that's cool. All right, so we have these, it's going to go down one plane and up another. We start, is it 9 meters up? Yep, so we'll start right here at the 9-meter point, right? 9 meters from the vertex. I'm just not going to draw that line. And then it's going to go down and back up to the 15-meter point, all measured from this vertex of the two planes, right? So we have some givens. It says it starts from rest. It accelerates on part 1. So we're going to say that's A1 is 0.5 meters per second squared. Okay. We'll also call that V naught 1 because we're going to have a part 2 to this. Okay, so everything on this side will be part 1. Everything on this side will be part 2. All right, now when it reaches the bottom, the ball rolls up another plane where after moving 15 meters, it comes to rest. So all we know on this side, VF2 would be 0 because it comes to rest. We also know the delta x's on each side. Delta x1, delta x1, and here we have delta x2. Okay. Now, question 1 says, what is the speed, I guess question A, what is the speed at the bottom of plane 1? So this is going to walk us through solving this problem. If you find this on your homework, take-home test, or a test, sometimes they just jump right to part C or D and say, what is the acceleration along the second plane? And then you have to think, okay, well, what do I need to solve in order to find that answer? Luckily enough, we're going to play it easy this time. So what is the speed at the bottom of plane 1? Well, we need VF1. That is the goal. We have V naught, we have acceleration, and we have x. We don't have time, so let's use the orange equation that doesn't have time. Okay? So we will use VF1 squared equals V naught 1 squared plus, what do we use, 2a delta x, 2a1 delta x1. And we need to know V final. It's already set up for V final. Let's put in our numbers. V final 1 is the square root of, oh, we can get rid of that guy. That's 0, right? So it is the square root of 2 times 0.5 meters per second squared times 9 meters. Okay. And that gives a V final of, I believe that's 3 square root. Yeah. Oh, yeah, we can just do that logically. Okay, so if we do 2 times 1/2 is 1, 1 times 9 is 9, square root of 9 is 3 meters per second, okay? So that is our answer to part A. The speed at the bottom of plane 1 will be 3 meters per second. So I will put that up here in our givens. We have 3 meters per second at the bottom of plane 1. Now we also get some new information there, right? If that's the speed at the bottom of plane 1, that would also be the speed at the start of plane 2. So we can also say that V naught 2 would be 3 meters per second. So we know that information as well. Now, part B, scrolling up, I'll erase that work in a minute. So if you need it, pause it. How long does it take to roll down plane 1? Okay, so now it wants time. So let's find time. So now we need time. Time for part 1. So we've got all of them. So let's use one that's pretty simple. We cannot use, so there are 2 that have time in them, right? There is V final equals V naught plus AT, and then there is delta x equals V naught t plus 1/2 AT squared. Now this one, right here, this one is not bad if you already have time. Because then you can just put it in, you multiply it, you square it, not an issue. But if you need to solve for time, don't use it. This is the one you need. Whoops, went off track there. This is the one you need if you're going to actually solve for time. So let me erase my scribbles. We will use this guy to solve for time. So let's solve for the variable first before you use numbers. You have v final minus v naught equals at. Then we'll just divide that a over, and you've got time. Now we can plug it in. Remember, v naught is 0, so you don't need to use that. You've got 3 meters per second divided by 0.5 meters per second squared. Dividing by 1/2 is like multiplying by 2, so you would get 6 seconds. So it takes 6 seconds to roll down part 1. So now we're starting to build our givens so that we can solve for the other half of the problem, part 2. So part C asks, what is the acceleration along the second plane? Now okay, that's something that we can solve for. I'm going to erase this work, so if you need it, pause. So what we have is we have v naught, we have v final, and don't forget we also have delta x down there. We know delta x. It's 15 meters on that side. I just didn't put it over there. So it asks for acceleration. The equation we're going to use is vf squared equals v naught squared plus 2a delta x. And remember, these are the givens from the second side. So we've got vf2, v naught 2, a2, and x2. Now let's solve for a. What we're going to do, that's messy. What we're going to do is we're going to take the v naught from the other side, subtract it over, and we'll divide by the 2 and divide by the delta x. Okay. That will give us a. Now on this side, v final is 0, so you can ignore that one, but the minus still stays in play. So you've got -3 squared divided by 2 times 15. Okay. So the negative gets squared away anyway. But our acceleration here, again, rough penmanship, the acceleration here is going to be 9/30. There you will have, oh no, that acceleration will not get squared away. It shouldn't get squared away. You're going to square it first and then subtract. It's a subtract, not a negative. I apologize. Let me erase my goof. Okay. That's how that should be written. The 3 gets squared and then you subtract it. So that negative will remain. We will get -0.3 meters per second squared. So that's the acceleration on the second plane, which if we compare the two is lower than the other one, which leads us to believe that the first plane might be steeper. But anyway, this would be -0.3 meters per second squared. Okay. So that's part C. Last part D, last part of this video. What is the speed of the ball when it is 7.5 meters up the second plane? So this is going to reinvent part of the problem here for us. Again, this is stuff that can happen to you in AP where part of the problem gets changed and your givens will also change. Okay. So, for example, what is changing here? It's asking us for a new VF, right? It asks for a new VF. No, I'm sorry. Yes. Yeah, what is the speed? So it asks for a new VF. What is the final velocity of the ball when it is 7.5 meters up the second plane? So now we have a new delta x. So let's get a little divider here. Our new delta x is 7.5 meters, excuse the penmanship, and we need VF. Now the V naught will stay the same. V naught, because it still went down the first plane and it's coming up, it'll stay 3 meters per second. And the acceleration will stay the same. Acceleration is still negative 0.3 meters per second squared. But we need to find VF. And we don't have time. So let's use the one that doesn't have time. We have V final squared equals V naught squared plus 2a delta x. Let's see, we have no zeros, so we can't cancel anything out, but everything is solved for us, right? It's already solved for VF. You're just going to square root it. So VF is the square root of 3 squared plus 2 times negative 0.3 times our new delta x, 7.5, all into the square root. And if we put that in our calculator, because that is too much in a square root for me to do, let's see, we've got 9 plus, I'll just do a minus, 9 minus 2 times 0.3 times 7.5. I got 2.12 meters per second. Uh-oh, that little gray bar there is getting in my way. There we go. So 2.12 meters per second is the speed of the ball when it is 7.5 meters up the second plane. All right, those are our practice problems for the orange equations. Let's see. Next up, what we will start going over is we'll start going over free fall. Okay, and I mentioned this before in another video, but we're not going to use blue equations as ASCII did last year. We're going to simplify it and just use orange the whole way through. But we will still go over the free fall problems, how to actually do the math with them, and I'll explain the reason why I'm going to avoid the blue equations in AP Physics.